All right, welcome to the Orifice Lab. We're going to run through how to run this lab and how to take measurements. We'll also be displaying the measurements that we're taking on the screen so that you can use those in your lab reports. So the Orifice Lab consists of a constant head tank over here. This has a outlet that we can change the height of. So basically we can adjust the amount of water in this tank and it stays constant at that level. So that way we have a constant pressure at the orifice, at the hole down here. So the orifice looks like this, except it's a little bigger. So this is the 3mm diameter orifice. We're using a 6mm diameter, but it's just basically a small hole. So essentially what we'll do is we'll fill this tank up to the constant pressure, and a jet of water will come out of the orifice hole. And essentially we can treat that jet of water as a projectile, and then use our projectile motion equations from Physics 1. We gotta remember those. We can back calculate what the initial velocity of the water is, and then using that initial velocity we can come up with our parameters for the geometry of the orifice. So I'm going to turn the machine on and you can see how the tank fills up. So there's a bit of a balance between having too much and not enough flow rate. If you have too much flow rate from the pump, you'll get, the level will maybe an overflow. Actually, this pump has enough flow rate to overflow the tank. And if there's not enough, then of course we're not gonna, the orifice drain will be larger than the pump inlet flow rate. But this is pretty good right here. So we're relatively stable right above the outlet. And it looks like we've got about 327 millimeters of head. A common question on this lab is what are the units on this? I already gave it away, it's millimeters. So this, like in many of our other fluids labs, has units of pressure in length, which is a little bit weird at first, but it comes from rho GH, and the H is what's given. So as long as we know what fluid we're talking about, the length is all that we need to describe pressure. So the next step after we get our constant head tank set up correctly is to take our measurements with these needles. So Maya's going to do that.
Great. All right. So in order to do this, we're going to place this sheet of paper. Hopefully you can still see all of these needles. May be hard to see in your view, but right now these needles down here are actually touching the water, and so they're disrupting the flow, which changes all of the physics. So we want to move these needles so that they're just above where that flow is. We don't want them changing what this projectile motion is like. So I'm going to go ahead and tune all of these knobs, and I'm actually going to have my lab assistant, Cordy, do that side while I do the other side so that we get this done nice and quick. So now what we can do, now that all of these needles are sitting perfectly above our projectile, we can go ahead and make marks on our sheet of paper, which will be our way of mapping what the shape of that projectile was. I can go ahead and remove this piece of paper, make all the measurements I need, and I'll have all the data I need to understand what the shape of this projectile is.
It's always a good idea to write the head measurement that you get on this. So I think I had said 327. Alright, so I'm going to talk about how I made the measurements from the data that we collected in the Orifice Lab. So this is the test page that you just saw with the 327 millimeter head. So essentially what I did, there's a couple ways to do this. So I've treated the first pin, which is this mark up here. So I've treated that as the 0, 0 point. And then I've measured down from that line how far each other needle measurement was. So the first one I measured to be 1/4 inch, 5/8 of an inch, 1 1/8, 1 3/4, 2 9/16, 3 1/2, and 4 1/2. And I've written those on the side there as well, so you can copy those down. One other thing to note is that in between each of these needles is 5 centimeters, so you'll need that as well. I would have used a centimeter ruler to help you guys from doing one more unit conversion, but all I had was an inch, so you're gonna have to do that on your own. I'm sure you can handle that. But yeah, here's the measurements for that part of the lab. Yeah, and now we also have to get a flow rate for this one. So it's a good idea to get the needles totally out of the way so that there's no chance that they're in the flow.
So now I'm going to come in with this flask here, and I'm going to use it to measure how much volume this orifice can actually fill. Meanwhile, my trusty lab assistant slash co-instructor slash spouse is going to come up with his timer on his phone so we can time how long it takes to fill a certain volume, allowing us to then calculate a flow rate. Ready?
Yep.
Steady, go.
So looks like we've got, I would say, 156, and that took 3.82 seconds. Let's try a couple different measurements so we can get a good average. Yep.
Set, go. Ready, steady, stop. This time, when I announce stop, it looks like our flask got to about 188, and that took
3.9 seconds.
We'll do one more measurement just to be safe. Ready, set, go. Ready, set, stop. All right, this time it looks like I'm at about 153, and that took 3.2 seconds.
All right, so theoretically those should all be the same flow rate, but I'm sure there's some slight variation. We'll leave it up to you to calculate the flow rate using the definition of flow rate. So the next step is we're going to change the constant head tank to a different level and then do more flow rate measurements.